The screen is clear now?
Yes, sir.
Yes, sir.
So it's quite readable also now by increasing the size now. Okay, fine. So I think we have started yesterday to understand about this curve fitting to a greater extent by
So this was what I asked.
yeah, now you can see that this is what you are going to learn now. Okay. And take a effect of the measured data error also into consideration. See, anyway, I'll start now from here. The mathematics is a little more detailed one, but what I suggest is instead of going through the entire mathematics, I just tell you how to do when there is a error component is given. For example, y error. For example, this is x value corresponding y. There is an error of 6 here. There's an error of 6.3, 7.4. Okay, here also 7.4 and 10.2. As this y is increasing, error component also increases a little bit. And this is the data which has been taken from this reference, which is available for you to refer it at a later stage, or you can select any other data which is already available, so that we are sure that what evaluation the numbers are reproducible and we get convinced, yes, what you done is right. Okay, so one is here we have learned this linear fitting, and then non-linear we have linearized it, but here it is linear fit only. But what happened now? The sigma for each data for y is being given. Okay, this is the variance, which means there is an error component that is available for each y is been given here. That has been taken along with the data. So the data are 13579. That's what your number 13579. The second parameters are this one 15.6, 36.6, 15.6, 36.58.2, 64.298.8. That are the numbers. And this is the sigma, which is an error component, ERR. I have written it as this. It's a 6, 6.3, 7.4, 7.4, 10.4. That's the error component. Okay, now this can be dealt in a two different way, where this weights should be taken for all the parameters that have been shown here for this sigma. See, for example, 1 by 6, 3 by 6.3, 5 by 7.4, 7 by 7.4, 9 by 10.2. For the x value, the weight of this has been taken there into your fitting. Similarly, the other parameters, the y, 15.6 divided by 6, 6.3, 36 by 6, 6.3. Okay, and then 58.2, 7.4, 64.2, 7.4, 98.8 totally. So this weightage goes into this, and then this data should be fitted linearly and extract all the parameters. And afterward, the procedure is same. But there is you cannot just take this data alone, leaving this, and then make a plus minus plot alone. That's not enough. So this should go into your computation through this variables x and y. These are the weight factors. That weight factor consequences has been taken by
That sigma is the error in that, or
this is the variance, which is an error in this.
Yeah, 15.6 plus or minus 6.
Yeah, that's the error which is involved in that. 36.6, 6.3, 58.2, 7.4, 64.2, 7. This is the error which is involved. Proportionately, it goes when the y goes also. Okay, this is what the data that you have, and this weight, this sigma should go as a weight factor into x and y, and then do the fitting. Correspondingly, you get the fit parameters in the form of a linear equation. That is what one should do it. Okay, this is completely different from what we have done, just doing this and making a product. Not enough. Parameters should also be evaluated with the consequence of this variance. Then only your fit parameters are meaningful, and then that will be giving a meaningful number. Then this is what the number that you have. You can have the corresponding errors involved in this m parameter and b parameters. So all such things that can be obtained. Okay. So how do we take this into this computation? That is, some details are given, and this is little more involved one in terms of simplifying this. There are different ways that can be done. He is described one of the methods, but we don't have to really worry about this, how this is being implemented. But it's simplest thing. There are two different ways one can do it. One is you can try with the linear model fit because it's a linear function, or you can try with the nonlinear model fit also. Both are providing the same results for all the parameter, whatever you are going to extract, that can be confirmed now. Okay, this is what my X data for this set of data where I have listed list of list contains, you can see 3 numbers in each list. And one of them is error, other 2 are the parameters, the X and Y value. Y parameter is this, which I have taken it from the data again, that is use this double bracket and get that is separately X and separately Y. And you have the data pair, which is by taking, because I don't want to take the error right now here, but I have the data which is available here as it is, and the error component is below that again, that I have taken out from this data set, where I have taken the third component of that data I, 3, that picks out all this error component. Okay, 6, 6.3, 7.4, 7.4, 10.2. 6, 6.3, 7.4, 7.4, 10.2. That has been taken through this data error, and then data pair has been taken, and independently if required, that can also be used. Because we may be required in some places, otherwise you can ignore, and pair is taken, just take the pair of those data. Okay. Now, idea is very simple. This error component has been taken through weights in the linear model fit, and then variance estimation also given this form. So this is something which can be done, which is equivalent to mathematics, what I is going to describe here, and that consequence has been considered through this variation. You can see the data pair alone you have taken, but weight factors have been already taken through weights. Give this 1 by r square. This is something like what has been done here. You can see these weight factors are going through this. That has been taken through this variable 1 by of e r square. The variance estimation function also, which is need to be considered, because variance estimation is also required when you do this analysis when you have the weight factors. Okay. Now, linear model fit. Take a data pair, and here you see the way in which the variables are given. So this is only one parameter. It's like in x, comma x is given, which is linear fit automatically. If I have 2 variables x, comma x square, then corresponding 2 parameters should be given. It will evaluate automatically. So when you are giving the linear model fit, correspondingly you make sure that it has been given appropriately as a mathematical code, how it is being used, how it is being defined, that should be given like this. Okay, but you add this weight factors along with that, with this statement that goes into your computation, which gives the result. You can see the number what we have here, 7.12158, whatever you have done with all this manipulation, you are able to get it 7.122. It is 7.122 if I approximate it. This is what the number. And this is an intercept. Next
so
is
where
9.
is the plus or minus error bar in that fitting?
That has already taken into this. It goes into this.
Okay.
See, weight factor now. Weights.
Yes, sir.
Weights has been given for the each parameter like this. See.
Okay.
See the weights here.
I found, but the fit A0 plus A1 next, A0 plus or minus some value would be there.
That automatically plus or minus, we don't have to worry. Plus or minus goes into as a weight factor into it, and then it evaluates it. See, this is a weight variance, is a weight factor which goes into this. A weight factor, how much is going to be variation, the consequence of that sigma on this y and x, that will be taken care through this one weights 1 by e r square. That's the error component. Okay, so this takes into the effect of converting data in this form, and then it does the computation and gives the result. That result has been confirmed here. You can see here m parameter is 9.0 3725. That is the number which is produced, which is, if you try with this alone, leaving this error, you have a completely different result. That can be tried now. We'll show that. That will be fit parameters that are completely different from what you are getting because of the weight factors. Okay? Because that will give another confirmation for us. This weight has been taken into consideration. You understand what I'm trying to say? See, if I take this, leave this part, X and Y, do the linear fit model, okay, and then fit it, then put this error on that. That doesn't make sense because you are not going to take the effect of that in the X and Y and the effective value of B and M because of this variation in the sigma. Okay, that should also be taken into consideration by taking it as a weight factor. That is what the result that you have. We will see that when you evaluate the linear model fit. Maybe you can see here now afterwards. And then you see what's the difference between the parameters, what you get now, and with the considering only X and Y without this weight factor. Okay, so this weight factor should go into your data analysis part through these weights. That is what the meaning of this. Okay, so maybe we can do one thing now to make things clear now. We will do this linear model fit once. Okay, and I wanted to, you can see the fourth and fifth data is the A and B parameter. Where is the data now which we have, X and Y we have. We will do it here itself now. I have the data. It's fine. This is X, this is Y. Then I have to just take copy and paste over there for a linear model fit and then look for the, where is the linear model fit? If I take it now, I'm not considering the weight effect of the weight factor there. Okay. Fine. Now, linear model fit already entered and you are getting it. Now look at the numbers, what we have here. Fourth number and fifth number, 6.18, 9.7. Okay, you can see the difference now. Fourth and fifth are the A and B parameter. What you have here is 7.12158, 9.3, which is 9.7 here. Okay, if I do that, that will also show fitting. Okay, you can make a plot with these parameters, put the data, and then data error will be shown. But we are not going to consider the effect on the A and B parameter. Okay, that is what has been considered here. Well, so now you have a X and Y with these parameters, 6.8, so 9.7, and this is what your correlation coefficient. But we have then other things as usual, which can be checked now. Now here, I am taking a data pair here with the error. This is what the result that I have. So this is attempted by taking my fit linear model fit. You can take non-linear model fit also. So now my fit linear parameter table. You can see here estimate standard errors. This is what your estimates and the standard error for the parameters. Two parameters which we need. No, that is first parameter is the 1 and t, which is like a linear model now. And this is the, of course, t statistics and p values are given. So I don't have any idea. We have to really look into it and understand what it is. But this is the standard error that has been given in the parameter table. Do the nonlinear fit model. Functional form is not like what has been given here. You have to give what is the parameter name, C and M, C, M. And I'm getting the C as 7.121158, which is same as what has been found, and 9.3752, which is also identical to that what has been obtained with the linear model fit. Then my fit N, nonlinear fit, parameter table, they are one and the same. I don't see any difference with any of the digits in that. In fact, they are exactly the same digits that you have. Okay. Okay, what are the errors now? That's 5.8728. That's what has been found here. My fit left, my fit L linear model fit error is 5.87728. That's what the error which has been given here. This equivalent like a sigma here. And my fit parameters for the Second parameter is 1.198, that is what the number. Do the nonlinear fit again, same. Then my fit L, best parameters. Of course, this is what the best parameters we have. Same thing. Can find out independently. Here, these names are defined, C and M, when you do the nonlinear fit. Whereas here it is not been defined, it comes out automatically. You just ask for the best parameter for the linear fit model, that both the numbers will be printed, which is already given here. 7.1215 at 9.3752, that's available here. It's a best fit parameter. Okay, fit residuals for a linear and a nonlinear model. They are also same. It is already being calculated. Because if you want to have ANOVA tables, you can also create these ANOVA tables. Okay, this is the degrees of freedom, sum of the square and mean square average.
So what is ANOVA table? Can you?
Analysis of variance table. Analysis of variance. There are parameters now. For these parameters.
What are their relevance? There are three parameters.
This gives statistical information about your data analysis. Okay.
Okay.
So analysis of variance and when you do the regression now, any data analysis, when you do regression, you do find this one. Okay, which provides all information about it. And this is not just for your I'll show you. We don't do a lot of other things which are not relevant to us, therefore we leave it as it is. But somebody wants to do statistics, know that you have conducted a course in the previous month, no?
Yeah.
The whole entire thing that can be done here with this Mathematica. Whatever they have done can be done very beautifully if they are interested to use Mathematica for statistical analysis. Okay, that are available here with all the parameters. For example, see, basis function, best fit parameter, data, design matrix, function, response, fit residuals, which I have taken, standardized residuals. Standardized residuals. This is standardized residuals, student size residuals. ANOVA table. This is what the thing which I have asked for it. Then ANOVA table, in which you can see the related properties, sum of the square error include. These are all the related to this. Sum of the squared errors include. These are the various ways one can take out the parameter and make analysis. Then you have the correlation matrix, covariance matrix, eigenstructure. These are all again available. These are all statistically regression analysis. All people will do it. Okay, for a given data, it's possible to do. And this is also another related parameters. Then you have the other related mean informations. So there are so much has been incorporated here, and depending on your requirement, you select things and then try to do it, and which include finally an R squared also. Coefficient determined by determination of R squared. These are all most of the things which are more closely connected to the statistics people. They try to do all this kind of an analysis where they don't have a functional form. They may not know, but regression they do it and bring out some functional form and make an interpretation. But whereas here we are having a functional form, assuming that this is being fitted with a straight line. Okay, functional form we are making it, and we are looking for the interpretation. Where there you have only data sets will be there. Then you try to bring it in the form of regression analysis, so that either it may be a linear equation form or a nonlinear equation form, and if it is nonlinear, they will try to go for some interpretation. Linear means some interpretation, like that they try to do it. Whereas for us, we have a specific data with the measurements which follow certain laws or a rule that we will try to extract out by assuming, yes, this is behaving like a straight line behavior is being observed, and then we try to interpret the result. See, this is a sort of a straight line features. Okay, with an error of plus minus that has been shown. We try to make some interpretation. Okay, if it is a non-linear, linearized form, slope has information, like what we have seen yesterday, there is a slope has information. Yeah, I think this is, I have to run this one. Okay, this is linearized, and we have a slope has information. That information also can be pulled out by analyzing the data. So all these things are possible when you have the ANOVA table. analysis of variance table. That's what it means. Unavoidable. This is completely statistics. They are very much depend on that. Okay, so he has given option for that, and this is the linear models. Exactly same thing happens with the non-linear model also. You can see here non-linear also have functional form, how to give the inputs, and then other options. In fact, he must have listed out all. Maybe in this other one I can show the linear model. Somebody has listed out what are the options that are available that can be seen. Scope options. Confidence, you can list out that all the options that are available for the nonlinear models. Working precision, weights, confidence level, I have seen somewhere that has been. These are all given independently with explanation, and that options are listed somewhere continuously that can be seen with the nonlinear models. I don't know where it is. Let me try to check. It's here. You can see there. You're able to see that? After fitting, now this is LM is fitted.
Yes, sir.
What are the properties that are there for the fitting now? Linear model fit. No, you have this LM that has been fitted. Where is it? LM, norm, ANOVA, MOM, DM. Where is it? So this is the model. Is fitting LM, linear model fit. What is the TS taken? Range number 1 to 10. Okay. His data is 1 to 10. Then that is fitted to square. This is what is the data. Okay. That is fitted to square and variable is x. And you can see this square of that, and this is a very small value. Okay. Anyway, what is important is that LM is defined as a linear model fit, and all information that is required for LM properties are listed out here. This many number of options that are available. We are not going to explore all of them. Only limited things that we are going to see. Okay. So you can see this ANOVA table here. You ask for it, that will be given for this data set. And ANOVA related things all are here. Then best fit parameters. Okay. Then some capture matrix, coefficient of variance, scoop distance, and correlation matrix. Everything, whatever you need to have that are available. It's depending on your requirement. If there is a need for you, just take out, give this name, give the corresponding name that you will get. For example, LM is fitted now. Okay, I am just getting this. LM is fitted now. Then I want to have ANOVA table for that. What you have to do is just copy this and paste it over into this property. Okay. So let's see. This is ANOVA table. This is ANOVA table for it. So then you want to know further what is each one of them. Then you refer to statistics. What is the degrees of freedom? Then sum of the squared value, mean squared, F statistics, and the statistics like that. It goes on. Okay. Then the error in that total is given. So like this is possible, and you can select the variables, and this is what he's trying to say, properties. Huh? Yeah, this is what thing you will given that, and you are getting all those parameters. You can select the best parameters, eigenstructure table. Okay, which we are not even familiar. Many of them we are not familiar. Maybe the statistical people can use all of them. Fit residuals we will use. Okay, function is available, FE variance, then parameter errors. These are some of the things which are familiar. Other things, no, we don't bother to look into those things. Okay, so this is how it's being done. Now table mean squares. Then this is of course simple model thing. Table equations. This fit residuals can be plotted like this also. Actually, after fitting it, how much is the variation with respect to the actual value plus fitted function? The difference can be shown that this it is minimum, which means your fit is good. Okay, with the measured data and this measured data and the model, then there is a minimum, means for the good result. Okay, so now you can see here now. This we try to explore, and when you have the data error, please make sure that this the factor effect that should go into your calculations. Okay, and then fit the parameters. Okay, now let's try to start from the beginning and try to see whether this is going to work here or not. Should work rather. This is X and this is Y. Linear model bit which we already done it. This is the pair of data. This is the error here. So my fit left side, the linear model fit. I have the numbers and get the parameter table. We are able to get it now. Now we'll use the non-linear model fit. Function change and we have the same. Put it in the my fit with parameters. Right. See? Left and this is not there. So we have linear model fit. So we are getting the parameter errors. Non-linear, again errors. My fit should be here on the side. Test parameters now for the linear fitting. And here it's possible to get the independently, of course, can pick out that. Fit residuals for the linear. Okay, this is what the results that you have, and this is that the this is linear on our table, and we try to see what happens with this. So we over here put non-linear model fit. So this is what the now what table corresponds to the non-linear model fit. This parameter, this is not being given here. R squared with the linear model is there's a slight difference. I do not know. We have to really cross check whether this is better or this is better. R squared seems to be linear model fit is not so good when compared to the non-linear model fit. This seems to be much better. This is I fit linear. Look at the matrix, covariance matrix, which we have to learn what it is. I don't have much idea about that. And this is the N, they are one and the same, linear and non-linear same. Okay, now when it comes to the plotting the error, it's very simple to do it. It's just see. I have this data, what I have given the first step, this is X, and this is Y. Add plus minus error I. So for every data of Y, there is corresponding error. Okay? I think is it clear for you? You can see here. Create the table now. That this table will show you. Let me take out this and see how the table looks like now. Okay. This is what the table. Okay. So now when you have a plus minus of that number, that will be taken automatically as a so-called the error in the data. And this is well, I will make it linear. Okay, let's make the normal form. And I'm going to plot both together. Either you can have a my fit as a linear or non-uniform, it doesn't matter because all the parameters are same. And this is what the result that you have with the corresponding errors. So you don't have any difficulty in doing the analysis when there is an error also. If you can write independently, go through the other texts and then without depending on the mathematical code, if you want to understand, then you have to learn little more mathematics. Okay, and refer these books or any other books where there is a with the errors analysis given. That if you follow, then all the numbers whatever has been given can be produced, and then use the mathematical code like this and reconfirm it. So now almost we have reproduced whatever has been given here. M, B, and sigma M and sigma B. This number had to confirm it. This is something connected to the covariance form that we have to look into it and then find out what it is and get that number also. And you spend extra time on that. Okay. Now, this is the. Now, if you have a large number of data with all errors, it's possible to do just by adding this plus minus error. So, if you have any data sets with error, just keep the error separately like this. At the end, you do this reading with an addition to this X or a Y. So the analysis, make a fit. This is fitting with the error. This is what the result. So these are the data points with corresponding error. And okay, so I hope this is clear for all of you. And you try both. Even if it is the equation is linear, you can fit with the non-linear also. That's the point which I wanted to emphasize here.
Yes, sir.
It is not necessary that when you have a linear data behavior, I should use only linear model fit. You can use non-linear model fit also and provide, because non-linear model also basically uses the similar idea of linear model fit. Okay, so therefore you can use either this or that, or when you try with this linear or a fit and find fit, these things will be missing. Okay, for example, parameters, parameter table, ANOVA table, okay, parameter errors, this may not be, you may not be able to get, which means the regression part may not be available, all of them. Only certain regression part will be available. If you really go for a linear model fit or a non-linear model fit, all regression parameters are available for you to take it out for the corresponding fitting, whether you use a linear model or a non-linear model. Okay, and also make sure that when you are giving the function, when you use the linear model fit, you see the functional form how it has been given. Okay, whereas here I have data P, but you should actually given this. And if you have more data, okay, and you need to have an input approximate range of this parameter, that should also be learned, that should also be given. Because here the data are simple, so it can select the parameters nearest automatically and then does the fitting. But there are situations where you need to define the range over which you wanted to search for this parameter C and M. So if I give somewhere between 4 to 8, this one somewhere about 7 to 10, that should be, it's given, easily it can find out. But here in this case, it's not a problem because data are so simple, automatically it searches for it and it gives it. But there are situations, I'll show you some of them, where you need to have nonlinear fit model requires or demands that there is a requirement for you to provide the range for C and M parameters. Or the whatever the fit parameter that you have in this, that should be range for the parameters should be given so that it will take automatically and over that range and search for the fit parameters. Okay, so that is also should be kept in mind. We'll see that. I have some of them. I will show you how that we will be doing it. Okay, so this is clear for all of you. I hope. Fine. So far, so
Yes,
good.
sir.
Yes, sir.
So now you can explore it. Now, what you can do, one more thing also, whatever which you have done linear fit now using a linear fit, whatever which you have developed here, that can also be tried with this non-linear model fit, linear model fit. But these are all not necessary. You don't have to, because there is no weights available. You can fit it and then get the same numbers what has been given, what has been obtained. These numbers. Okay, maybe these numbers can be found easily. So which means I can use for a given set of data, fit can be used, fine fit can be used, linear model fit can be used, non-linear model fit also. There are 4 different ways that one can really handle the data and see that analysis can be carried out. Get the point? Fit, fine fit. Then you have a linear model fit, non-linear model fit. For any given set of data, you can make an effort to do the analysis. So now we have, when you have an error, you don't have to worry now. Please remember that this should be taken care. Otherwise, your parameters may not be agreeing with the parameter what you get. For example, if I do linear fit, my parameter is this. Okay, 6.18, 9.7. Whereas taking the weight into consideration, this is what the parameters. These two are parameters. They may not match out. If you wanted to check now, this, let me show you what is going to happen now. We have the, I wanted to show you this. List plot. List plot, what you want to plot is the pair of the data which you have here. Maybe I can take this as a data. So this I'll put it below then because get it cut and paste over here. I'm putting it here. Okay. Next is this has been done. Where is it? We have done the linear fit. X and Y is available. So we have to make a plot. What is the plot now? Should be 7.6.83. Maybe select one by one. So that I have this parameter. Okay. Plus the 9.7 with the other digits also come more. Let me take as a variable, some variable u. Okay. So plot this for the range of u, so 0 to how much is the 9, so to 10 I can go. Okay. Plot u is varying from 0 to 10. This is what the result I have now right now. Okay. So this should be show together. Close it. Show together. Let me show this. Okay. You have it now. So this also follows the same. Okay. Similar structure is there. And in this, if you wanted to add the data with the error also can be done. But your data analysis is rather incomplete or it's not proper. That's what it means. Okay, go. I'm going to show the same with the error also, linear number fit. Here, where are we now? We are here again. And I want to add that with the error now. Okay, and the plot this one, and we can see both together. What happened? Table, error. I have to do. What am I supposed to do? I have to do. List plot should be taken into consideration. I have taken the data. I'm trying to combine the data and the plot. So that's going to be a problem. So I don't see any difference between this and this when you look at it. But actually the parameters are different. That is what the point which I want to do with your consideration. Okay, so if you wanted to reduce this one, we can do because 99999 is almost 618. This is 6.7000 takes up to the number. Is enough. Okay, you get the point now. So usually this is what people will try to do without taking the effect of that into your fitting. Okay, and now you can see that this is going to be a range of values for the parameters because it has certain standard errors that's involved along with that. And then that should also be considered now, and we describe that. And then yesterday I was trying to show something to increase the x-axis and y-axis sizes of this scale, no? That what you have to do, I was struggling yesterday, but it was simple. You have to do now axis style. Okay. So, axis style, you give a number. So 14, if I make it, you can see that x-axis, y-axis numbers become bigger in size. That's the option which I was trying to do yesterday. Axis style is 14 means it will become bigger in size. Because yesterday I was trying to search for that. So this is 12. And if you make it something you want to bring down the numbers, so let me do 8. It's small. So if I make 18, this will become 2 big. Okay, so this is control over that. To control this so-called numbers that is appearing in the x-axis and y-axis. There are other options also. There are so many other options which can be explored. And I want to make it 13, which is other reasonable. Other things we can add. So this also I just given it here now. Please remember that when you have this list plot, okay, axis style can be controlled. If once you make a frame, then this axis style will not work. Then you have to think in terms of the frame. Frame whatever the options that are available. Okay. See, for example, let me write frame. What is the frame? It's true. Okay. You can see the letter has changed. Okay. And if I change this, say 15, is it going to change? No, no, doesn't matter. It's not going to change. Then correspondingly with the frame, what is the statement that is required for this change in this that should be taken into consideration. So don't get confused that when I put a frame, this is not size, is not able to control it. Okay, so even if I put 3, I'm getting the same thing. Okay, whereas if I remove this frame means I'll get this complete structure of this figure in this rectangular form. Okay, so if I remove this frame, you see that number has become invisible now. And now it's become visible now, and there is no control when you have a frame. Correspondingly, frame should be defined, and also frame label should be not axis label. Once you have a frame, it should be frame label. So when you use frame, corresponding frame related options that should be explored. Okay. When I have axis, I have only x-axis and y-axis. There is no frame. So the corresponding that should be taken care, and then see that that is consistently varying properly. Otherwise, it will be a mess to have axis and flat style are frame will be different. Frame label is different. Okay. Here it is a plot label. There is a frame label. So all when you have a frame, correspondingly you have to take care of the options with the frame. What is to be done, that should be taken care. Otherwise, you have a confusion. Okay. So that's also important point, because you will try to have when you write it in the frame, then when you wanted to have a control over this for x-axis and y-axis, if I write, that's not a plot label, frame label. Then frame label should be given properly. Okay, so those things you take care of it. So this is what the pictures that you have after fitting, and these are looks pretty good now. And when you have errors, please don't do the analysis like what has been done here, linear fit model. It appears to that you have done the analysis, but actually variance of the parameters are quite different. Okay. There are other further analysis also possible, but what is the range of the parameters that are there for this error what you have incorporated here? For this error, okay, what is the range of parameter A and B, or the M and B allowed, and how does it going to affect your fitting procedure? That can also be analyzed. So these details are available in this. You can go through this text. Nice text for numerical analysis for engineers and scientists. And I think that this is a lot of other interesting topics also, which can be referred. That will be useful for you. Okay, let's go to the next part of it. Well, after that I have done here. We have linearized this, and then we have done something. So maybe I can just repeat this and check. Linearized. It's been done. Function has been entered, and we did that. This is the result which we confirm. Well, okay, this is a linear form which has plotted, and this slope has information. That slope information is, you can get it. This number is the, suppose if you don't know that data are available, you do the fitting like this, and then analyze this, take the slope. That slope is going to give this information, because when you take the log ln, this is the slope. This line has a slope. That slope information can be pulled out, and this is what exactly we do with the so-called Arrhenius equation, which will be my negative slope. The line will be on the opposite side. So which means you have to change the data to minus e power minus, then look at the behavior. Okay. So that's what this line, instead of coming like this, data point will be coming like this. Okay. Take care of that. And now that is, if you plot actual plot, it will be looking like this. Okay. So this is what the results that you would get it when you got when you linearize the nonlinear law or nonlinear equations, and various types they are seen. You can practice with 1 or 2 problems, which is given in the Shastri book or any other textbooks, or your own problem which you have, which is exponentially varying. Number of places you would come across this exponential behavior. Okay. Right. Now we go to the polynomial fit. Now, as I said, it is again similar, very easy to follow. Okay. Then modify this, the polynomial fit, and then take this typical example of this polynomial fit, obtain all the parameters, do the polynomial fit, get the parameters, try to analyze and see that you're able to get the parameters like A0, A1, A2. See, here is the small important observation which I would like to draw your attention now. This method, of course, it will be easier. Again, this is just extending further terms. That's if you have a square of that, you have a 3 by 3 matrix, and that should be solved. If it is 4, then it's going to be 4 by 4. Of course, this number of data points is more than corresponding that size of the matrices will get changed, and that all easy to do it by just by using this transpose of x dot x and transpose of x dot y. This will take care of your requirements, whatever is needed. That will be done automatically. You will get these numbers that can be produced. But here I wanted to draw your attention. You have CC 0, 1, 16, and 217 is the data which we wanted to fit it by using the polynomial fit, where we have taken up to square of that, which means I have the polynomial fit and it has an x and x square term with a constant. Okay, this is what the number which you have. So let me exclude this first polynomial fit and get the correlation if necessary. You can have it. Now, the first data is what is the data? 0, 1. Let me take here 0, 1. Ah, 0, 1. 1, 6, 17 polynomial fit with the list. Okay, list is 1, 0, 1, 2. That's what this is. The first list. So list has to say given 0, 1, 2. That's the x. Because 3 data are given as it is. So writing a data and then pulling it out. Then for a 0, there is a 1. For 1, there is a 6. For a 2, there is 17. Okay? Is it right? Are you able to see this? This is
Yes,
x.
sir.
This is x list. This is y list. And number is 3. Okay? Data numbers are 3. That's what the number that has been given here. And of course, this is if you have a small number 10 power minus 15, 16, that will be automatically eliminated. Now it doesn't make sense now. Now you see what's happening now. If I give this, you have an error. Okay. 0.0 is encountered. 0 power 0. So there's going to be a problem. Indeterminate is created and it's not going to give a result at all. So there are 2 ways to avoid this. Number 1, you change the data to the next point. For example, instead of 0 starting, you start from 1, 2, and corresponding number 3rd. You should have some idea about what could be the 3rd. Otherwise, it's not possible to get it. Otherwise, what you can do, this 0, instead of taking 0, you take it as 10 power minus 16. This is almost 0. Is it not? Agree with me?
Yeah.
This is 0. Okay, if I do this, I'm getting the result. The fit parameters are the, where is the fit parameter? Here. Solve transpose, solve x, x and y, dx, dy, print these things. Fp. Fp is automatically give that number. So you have the output, print form, what are the things they are asking? This sum is right. This is also, so this is being calculated for the correlation. And we have this print parameter. When you export it here, automatically you are ending up with the parameters of Fp. Table of that. Okay. So this which will give automatically the numbers what you need as a fit parameters 1, 2, 3 in this case. 1, 2, 3 in this case. Okay, intercept is 1, it's not intercept, it is actually 1 plus 2x plus 3x square, which will generate this table. And if I know that, I can go ahead with this 1, 2, 3. 1 and 2 correspond to 6 and 17. Third, 3 is equal to 34, and then do the analysis. I have the same parameters now. 1, 2, 3. Only these numbers are different. I hope it's clear for you. See, instead of taking 0, 10 to the minus 16, I did start from 1, 2, 3, that's x value, up to 3 instead of 2. Then you know the first value is third parameter also I have entered it. Then do the analysis. I find that the fit parameters are same. So these numbers are different. There's no connection between this number to this number. But my parameter 1 to 3 is same. Okay, because this can be used, you can select the range of the data from any starting point. I can have starting from 3, 3, 4, 5. Or you can have a 3, 6, and 7. You get the point what I'm saying? This is the x and y after fitting in this parameter which you are able to get in. Now what I'm trying to say, I'm generating the data starting from value of 6, starting from 3, 4, 5, 6 or 3, 7, 8, any combination. The 3 data can be selected and then use that, then analyze it. When you do the analysis, you get 1, 2, 3 only as a fit parameter. For example, I can generate this table now. You can see what's going to happen. 3 data I'm going to select now. I'll define this y of t. Okay, this is the data I'm going to generate now. This 1 plus 2t plus 3t square. Okay. Now I have a data set now. So I want to have it as table. You need to have y of t as a function of t. T will be there, and y of t is going to be y t, which I'm going to change the t. First set what has been done is can do this. Of making the table, I'll give 3, 3. Because we are going to have a different values of these. 0 is 1. Then I'm going to make a list for 3 times. Second data, third data, 3 data. 0, 1, 2, that's given. What happened? Can you guess? T should be put with the rule. Substitute for T as but this is not the executor now. Do it now. Okay, I have the first set of data which is given here. 0, 1, 1, 6, 2, 17. Now I just copy this, edit, copy and paste over there, and then change the orders. This I'm going to make it as 1. This is 2. This is 3. This pair of data also I have the same constant. 1, 2, 3. If I do that, that's what has been done here. 1, 2, 3, 6, 7, and 34. Now I can select some other pair of data. It need not be the same order. We'll take somewhere about 3, 4, 7, 8. What would happen? Do you get same thing or not? This is the number. No? Sorry. Did something wrong here. This must be start from 6. This is 8. This is something like 10 also. With the numbers. This is what the number I have. Okay, for this pair, if I do the analysis here, polynomial fit, I want to try. Do you get same value or different value? Ready? copy over here. What is the number which is generated here? And third, 621. 121. That's the y. Next is 8 209. 8 plus 1 to 209 and 10. And I have 321 is the number. 321. Okay. So this is completely different set of numbers. For that, I wanted to check whether this is your 1, 8, 10, 1, sorry, not 1, 8, 10. I think I confused here by using the other table. First number is 6, 121. Here I made a mistake. Sometimes you make such mistakes and then struggle for correcting it. 6, 121, 8, 209, 10, 321. See? Okay, I did same changes here. Okay. Now, if I enter here and do the analysis, I'm getting the same number 1, 2, 3. So, that range for the functional changes, now anywhere in the region, now, if you try that, the coefficients what you are getting is the same, that these numbers are completely different. So this is an important thing to note. Okay, because it's part of this function. Anywhere it's going to work. You can select any numbers which you have. All the time when you analyze it, you will end up with this number of these coefficients. So this polynomial is going to be 1, 2, 3 for any value of x and y. That is what the beauty of this function and its behavior. Here I will just correct it now. 1, 2, 3, 1, 6, 7, 13. Same 1, 2, 3. Fine. You get it. Now, suppose if you look at the correlation for corresponding all the three, then this number also must be same. Okay, correlation must be same. I want to check whether this statement is right or wrong. How do I check it now? I'll take 6, 8, 10. I changed it here, but I just smashed it so that I know the number. Next is 121, 209, 321. Okay, let's see. So this correlation changes now a little bit. That's when you go for the higher numbers, correlations seems to be better here because maybe this is correlation, this number is different from this. So we have to really understand this correlation and how this correlation varies when you change the range for the same function. When you go for a different range of numbers, the correlation get changes. So this is another important thing that should also be noted. How I mentioned that correlation must be same, but that's not the case. Variation in the correlation that's happening when you go for the higher numbers, for example, 6, 8, 9 as an x corresponding y. This is for this 1, 2, 3, 6, 7, 14. So this again I enter here for the comparison purpose. I'll just try to take 1, 2, 3. Then I have 6, 17, 6, 17, 34. Correlation here is 984925. Here is 99223. So we have to understand a little more on this correlation aspects of it. Okay, that's how it should be. Maybe for the first data point, if I do the correlation, do you have any error at that time? That also I can check it. Add here 0, 0, 1, 2. The numbers are how much? Where are you? 1617. Just add 1. 617. Oh, see, correlation changes. Quite different. So there is something to do with the consequence of going for a higher numbers for the same relations. The same relation, but I'm going for a higher number, and then when I analyze it, the parameters are fixed, but correlation changes. So it gives some indication that something happening in the correlation. Okay. So this is about the polynomial fit more than 2 variables. Intercept, slope. Next is the, here it is square term, linear term and that square term. That's what the result that will come. We can try with the other functions that are given. Okay, this is for the thing that I could have to do. Next is we would like to visualize this linear and polynomial fitting. We may using the manipulation of the data, and we can have the data addition is possible along with this. Can add more number of data also, and the number of polynomials that can be added also goes up to 6 polynomials can be used for the data analysis simultaneously. So this is manipulated for the x starting from 0 to m, which goes in terms of the polynomial degree. And we can start from 1 to 6 in steps of 1. To start with, you have a 4 because it is entered as a 4. And if you shift enter it, you will get a 4. Before that, this should be x all has been defined there. So we will local fit locally. By this process, the whole thing will be redefined. See, all have become fresh inputs now, whatever you have done here so far. And all other things have been vanished. Input, output, and fresh one. This is number 1 now. This is degree of polynomial. So this is what the results that we have. If I have this, okay, 1. Now you have an option. See, this is the equation of a straight line. So now what you can do, you have an option to locate, which means I can pull out the data the way I like. Okay. I can bring the data close to a straight line. You see, this one data does the line fitting like this. If I bring this to this line, it's, you can see the consequence. Amazing. This is the equation of the straight line, and you can see the consequence of changing one of the data points. See, for example, this one data, this is supposed to be there, but we are retaining this, and we are when you do the fitting, this is what the fitted line.
Oh, so this is really
so it's dangerous. It is dangerous. This fellow is odd man out. It should be removed when you do the fitting. Don't try to do the fitting and then try to interpret your results. You'll get some rubbish. Okay. This fellow, if he falls on this line, you have a meaningful information. Otherwise, it's meaningless.
Yes, sir.
So that's why when you do look at the data, make sure that there is some consistency in the process, either in terms of a square of the behavior or a straight line feature that is there, that should be taken care. Otherwise, this is what your consequence.
So this happens in dielectric spectroscopy when
Number
high
of places.
frequency above 1 megahertz.
Not only dielectric, number of places in physics. One should be careful about, and even a little bit. See, this one data deviation will affect very badly. Okay, so that's why your measurements and other things should be very careful. Now there are 2 process means that should also be taken care. Okay, I can have a 2 different process in the system, following one system, one type of a behavior over the temperature range or over the temperature of the parameter, and then other behavior. That can also be taken care. It should be taken care. So Suppose I have one set of data here. This is following like this. I can have another set which will be having completely different kind of a slope, which can be following like this. That is fine. But when there is something happening here, this fellow is here, then it's going to be danger. Okay? This should be taken. You have to really look for it because it is a linear scale, it doesn't matter. But it is a nonlinear like logarithmic scale, if it's there, even the magnitude become too high. Okay? Normally this Arrhenius plot will be log, no? On the
Yes,
y-axis.
sir.
So that should be very careful. Even minute change matters in log scale. So those things should be taken care. So for example, I'm going to add another set of data. How do I add it? It's very easy. For adding additional data points, press Alt key and then press Alt key. I'm able to add this new data. This is already there. Okay, I think simultaneous fitting of two lines has not been given, so therefore it's not possible for me to see that. But anyway, I can have another slope like this, which can go. See this option, no, this is a limitation. Two lines.
Yes, sir. Two
not
lines.
been available.
Yeah.
So that's the reason I am not able to do it. So now, if you take all of them to that point, then your slope will be. See these two. It's affecting very badly this line, and they take it to this
Yes,
point.
sir.
This one fellow, you see how much is the fees. Okay. Get the point.
Yeah. Yes, sir.
So therefore, one should be very careful when you are doing the analysis, and particularly try to fit like this and extract the physical process. So this, if this is there, then you try to say, then you will have a problem with this interpretation. So therefore, when you have this much deviation, it implies something must be happening in the system. Otherwise, it's a measurement problem. That should be picked out immediately by looking at the data. So if this is right, if it is really following that line, then you really feel that this will be, and you can see that. Fine. Now I can bring the data here. Okay. It's another kind of a straight line that you can think of. See, now it has been taken both the data and fitted this. Okay. This line, no, what you have here, it is considering this and this together, this has been taken the fitting. So now this is somewhere here and then put it over here, put it over here. See? So this one data, if it is here, and then if you keep it here. Okay, so this is how things happen now. So same data, suppose if I try for the second order, this is what we'll be doing. So this is what we will doing VFT fitting now.
Yeah, right.
VFT is like this, and VFT when you are not, okay, how much is this changes? One data you see is pushing up, in fact. This fellow you see is going up. You bring it here.
Yeah.
So therefore, you should see that things are taken care when you are doing the fitting the data. Now you can think about going for the cubic. Seems to be still better. And again, the cubic when you add, even the smaller change, the consequences will be much bigger. Okay? Because your scale is limited. This is following like this, but one data shift, no? And see how much is being affected by that. Okay. Cubic part which is coming here and then goes up. There's no data here. The data are there. Suppose the data is here, it's fine. Okay. So this will help you to understand the behavior of the functions. These are the data points now. And this is the fit parameters corresponding. You have the x squared, x cubed with the weight functions now. And there's data. And this can be pulled out here and then you can pick it out here. So you can play with this and try to understand more about this kind of how the data influences your curves. That's extremely useful for you to understand it with respect to the polynomial fit here. Okay. So I felt that this is what should be discussed now. And I will send you this with the details further. All this further details. You can go through them. Then try to have some more understanding. And this is very important, particularly for physics students.
Yeah, really, sir.
It's really useful for students. Yes, everybody is doing experiments, and then there is a data, there is an error, and you do the data fitting and functional form, whether you linear form or it is a non-linear form. Linearization is also allowed. There are several functions which can be linearized. Okay, what has been given is only 4 or 5 types. But they have several functions which can be linearized and make a plot and extract the information by systematic analysis. Now you can see how sensitive is the data points, data are. Okay, keep that sensitivity in mind and then do the analysis and make sure that you are coming out with the proper interpretation for the numbers what you find with the features. So that's what one should do it now. Okay. I think this is enough for the data analysis and
yes, sir. Yes, sir.
Most of things what is needed being covered. Okay. Fine. So, any queries, any clarifications you have? I'm happy to answer some of them. There are other fittings available like spline fitting. Okay, using the certain polynomial. See, there also it is no. Which when you look at it, you can get an idea what do you mean by the spline. You break it into small pieces and then use the appropriate polynomials and do the fitting. See, this is the sort of a spline thing. Now you can see goes up like this with this. There is a minus of x square. This is accommodating this, and you can bit you can do polynomial and fit it, and then overall curve can also be brought in. That's how this is other fitting procedure that will be followed, where you have a smaller scale, large variations are there that should be taken care by spline, dividing into small thing and then make a fitting and combine it overall and then get the overall fitting. So once you have this picture clearly, then other things will be easier. There's not much problem. Other things are again depending on the nature of the expression that you are going to analyze. Correspondingly, you have to apply the methods. And once you have this nonlinear fit properly, then you can have a great thing that can be done with the help of this so-called, where is it? Which we have analyzed now. This is extremely useful for you. This part. Okay. This part, what has been done with error, linear model fit and non-linear model fit. And most of the time it's enough. This table is required. Okay, which takes care of your standard error with the estimate of the parameters. Okay, and if you have error component, you add this and do the analysis. If there is no error part you are going to incorporate, then directly do the fitting with either linear model or non-linear model. Give the details in terms of this parameter estimate and the standard error. That will take care of most of the things. Okay, this is the most important thing. These two parameters, standard error and the estimate of the parameters. Okay, I wanted to show that some of the things which have been done long back. I hope I'll be having it now. 1 or 2, I wanted to show you how this is being done. The model fit must be there. Just check that is there, then I'll show you that model fit. Yes, model fit is available for you to see how things can be done. Yeah. This is one typical result which can be seen here, how this can be analyzed. The actual data also will look like this one. Therefore, it's possible for us to have a detailed analysis, but at least something which we can describe here, which will be useful to you. You see how the data that can be generated like as if we have measured the data. So we have a function of this type. You can see this is the del epsilon, some function, let's not worry about this. This is the variable that you have, the parameter is being taken, and its magnitude is 0.58, 10 power 0.58, which is represented in the base 10 of log. And this is the frequency which is varying for the exponent which you have 0.7 times. This is something like a Cole function, okay, dielectric function with the parameter of the del epsilon. This is the del epsilon. This is your time scale, which is here 10 power minus 3, and your exponent is 0.75. I'm adding the random error here along with that. Random real, which is going to be an error in this, that should be added here. Do you see how the data are generated here? Okay, easy to generate. 135 data are generated with this small piece of error along with this function, which is the imaginary part of it. You see, so much has been done with this one line state table log of 10 power f, which is the frequency. Okay, and it is something like you're going up to, this is random, which is to be shorted out. You see the numbers here. 1.4 is the initial value of the frequency. And next is 5.0, 10 power 5. This is 10 power 1.4. That's what it means. They are random because we made it as a random F. Okay. You see this number, first numbers in the log scale covering up to 10 power 7. Okay. You have somewhere about 5 is there. 6 also somewhere will be there. 7 also will be there somewhere. 0.4 also will be there because I started with them 10 power minus 2. 10 power minus 2 to 10 power 7. I am going in steps of randomly. That is why data are random. But if I plot it, they look like this. Okay. This is what the plot that I'm getting it. Now, this number, what I'm going to generate now, done. Generated now. 135 data randomly generated with these numbers, and there is an error that is being added here. And of course, if I enter this, which is going to be free from error, that error component is not been added here. And added, this is missing there. Without that, it has been taken and it's been plotted. This is what the curve, which is in log. This is log scale. This is also log scale. Minus 1.96 is starting. And it goes up to 10 power 6.8. Okay. We can see this will be ordered now. All the data are ordered. Okay, this is sorted the data. Same in data is available here, which is random for even the frequency that has been shorted out. Write it in a consistent form. Then they're making a plot of them for the point P75, we are making a shorted data is best to plot, give these variables and then make a plot here. This is what the results that you have. And this is the curve. And you can see this contribution of this error here at lower frequency and the higher frequency side. This is in log scale both. You can see this magnitude also small. And you plot this actual function along with this 0.75. This is, there's no exponent here. And there's an exponent here. If I make a comparison between these two, I find this is going to be without any error and no exponent. This is with the exponent. And this error is there. Now you use the nonlinear fit model for this fluctuating data, okay, and analyze it and get the parameter. You see that parameters are epsilon s is 0.55979. And what is the actual value? What I have given is 0.58. I'm getting the number 0.5578. So you can see this contribution of these errors. I'm not able to get an exact number. And this is 3.02, which is 3 minus 3. 10 to the minus 3, I'm supposed to get 10 to the minus 3. Instead of that, minus 3.02027 is the parameter. And this is 0.75, I'm getting 0.71. This seems to be very sensitive with this data error or the error that is contributing to the parameter. So this is the parameter. And we can make a plot of the fit residuals now directly and see this, how much is the variation. And this is what the data now, and the line is the fitted line. That's what the plot is. So you can see such a complicated function that can be analyzed without much difficulty, even by generating that as if that you have made a measurement of the dielectric constant. And the imaginary part has been taken as a data that has been plotted here and then fitted here. The fitting results parameters are obtained. This is the standard error here. It's very good. Parameters are much better now. But please remember, this is in the log scale variations. Okay, so therefore this 0.75 instead of 0.75, I'm getting 0.71. Suppose the same data, if I reduce the error component and reanalyze it, 0.001. And how much is this one here? 0.002. The error is 0.001. Repeat. And your parameter will improve. Look at this. 5.6, 3.00 has improved. We have come to 7.3 because the error consequences can be realized now. The fit parameter that goes down when you reduce the error component by reducing instead of 0.002, I made it as a 0.001. Again, this is a different set of data because when you use the random, every time it generates a new set of data. Okay, and number is 0.58. It's not 0.57 or you made it as a 0.58 is same. They're also same. Okay, we retain the same number. But that will be improving further because your fit residue is also improving. Okay? It's also improving compared to the previous fit residue. This fit residue 0.1 up to 0.1. And what happened here? Fit residue, no, I didn't plot it. Anyway, when you plot it, it's there. It's very small, getting reduced. Fit residues have been reduced. So as a consequence, now if I make it 0.1 not one more 0, then do the analysis, you are almost to the exact value. 0.578 is 0.58, 3.001, 0.747 is almost 0.75. And you are to the data. Okay. So like this, you can go ahead and add. See, there are two functions. You have complicated that, but
9:30 students are.
Yeah, just stop it here. It's enough. For them, this is more than enough. Okay. So we'll stop here.
Yes, sir.
We'll meet in the next session. Next session, when can we have it? Tomorrow, what is the plan?
Tomorrow, that time, maybe
Daytime, I don't know. I might be having some work the daytime. I'll confirm it
okay.
morning.
Yeah. What
Around,
time maybe?
around 10 o'clock, I'll confirm it. Around 10:30.
Okay. Or you can have it a bit.
Monday, Tuesday only. Then. The Saturday, Sunday, no?
Yeah. Okay.
Okay, we can plan that way, Monday, Tuesday. What about the students' convenience?
Yeah. Students can tell.
Yeah, it's Monday, Tuesday also fine, no problem for me. 2 more classes,
Vishnu
na?
Priya.
Sir,
Yes, you can tell.
What is tomorrow's? Whether you need a class tomorrow? We have 2 classes left, so we need to have a glimpse of partial differential
sir,
equation, and
Sure. Partial
then
differential equation,
and
eigenvalue, right?
eigenvalue.
Eigenvalue.
Yeah.
These two are important. Yes.
These 2.
Yes. You can change.
sir, tomorrow 2 p.m. we have another class.
Okay, then sir, we can have it on Monday.
Monday and
evening.
Tuesday night times, evening.
Yeah.
Oh,
Yes, sir.
fine, sir.
That's fine. Okay.
Thank you, sir.
Okay,
Right,
sir.
bye.
Good night,
Bye.
sir.
Good night. See
Sir,
you.
can you send the
I'll
materials
send it
now?
right
The
now.
two people.
Yeah, I'll send it now.
Yeah. Okay.